Hello again, and welcome to this new chapter to some case studies and projects. Now, the first small case study we are going to talk about is CAN bus sniffing and fault injection. Now, here is a detailed walkthrough of practical case study involving CAN bus sniffing and fault injection, ideal for bench level testing or simulator environment. So, this particular test is ideal for lab testing. And this is a fascinating idea that blends low level protocol analysis with cyber security and diagnostic validation. So let's see about it in a more elaborate manner. Project title: CAN bus sniffing and fault injection for ECU robustness. Okay, this project aims to evaluate the resilience of a ECU's diagnostic stack by sniffing live CAN project. Now, sniffing means it's like your this is a more local jargon for smelling. So you kind of have a sniff about the live CAN traffic, and then you inject faults and observing system behavior under controlled conditions. It is particularly relevant for validating cyber security access, read DTC information, and CAN error handling in compliance with ISO 11898, ISO SAE 21434, and WP.29. All right, now we will talk about this system setup overview in this table. What is the component and what is the role? The first important component is of course the CAN interface, because we are doing the CAN sniffing. And what does it role? It captures and injects CAN frames via socket CAN or vendor API. Next is ECU. All right, next important component is ECU, runs diagnostic services and responds to CAN traffic. Next is Python CAN or Cano. This is an important tool which is used for sniffing, logging, and injecting frames. With the help of via these tools only, actual sniffing and injecting frames happens. Next is fault injection tools. For example, Carpunk, SDAC. So it generates the malformed frames, timing violations, and CRC errors. So this is the actual tool which is generating these malformed frames, and Cano is a tool with which the injection this malformed frame is injected. Now coming to the oscilloscope or the logic analyzer, verifies physical layer anomalies and timing issues. All right, so this is the component which verifies the physical layer anomalies and timing issues. Now what is the first phase? In the first phase is a CAN bus sniffing. So what is the goal of this CAN bus sniffing? Identify active ECUs and their arbitration IDs. Next goal is to map diagnostic services and periodic messages. And third is detect anomalies or undocumented traffic. All right, so these are the three major goals of this first step. And how do you go about it? What is the actual workflow? Use Python CAN or Cano to log traffic on CAN 0 interface. Filter for diagnostic services 0 by 10, 0 by 22, and 0 by 19. Decode payloads using DBC files or manual parsing. And visualize traffic patterns and timing intervals. All right, now talking about this is the sample sniffing code. If you want, you can copy paste into this and you can use in the actual project in which you are doing. Now talking about the second phase, which is the fault injection. Now in this table we are going to see the various types of fault, what is the method used, and what is the actual expected ECU behavior. Now unless and until we are clear about the expected ECU behavior, the anomalies cannot be figured out. Okay, it is only when there is a difference between the actual behavior and the expected behavior we find out the anomaly. So what is the fault type? First is bit stuffing error. And second is inject 6 plus identical bits. ECU logs error, retries transmission. And second is CRC error. Modify CRC field manually. ECU discards a frame, raises error flag. Now talking about the arbitration collision, inject frame with same ID, ECU enters error, passive or bus off. This is the result. ECU enters error, passive or bus off. Now talking about the timing violation. If this is the fault type, and what is the method used? Delay, ACK, acknowledgement, or end of the frame bit. And expected ECU behavior is ECU detects from error. And talking about the malformed UDS frame, send invalid, SID or corrupted payload. Now this is the method used, and expected ECU behavior is ECU rejects request and locks a DTC. So whenever a malformed or a malfunctioning UDS frame is injected, it rejects the request and locks the DTC. Now, what are the major tools here which are used here? CAN injection, sniffing for real simulated vehicles, GUI based fault injection with pattern matching and arbitration control. Now, talking about the cyber security validation, this project also evaluates CSMS compliance under WP.29. I clearly explained you what this acronym CSMS stands for in the previous slides, and unauthorized diagnostics access attempts trigger. Now talking about the security access lockout, the fault injection simulates DOS attacks on CAN bus, logging and anomaly detection validate forensic readiness. All right, now talking about the outcomes and learnings, identify vulnerabilities in ECU error handling logic, validated robustness of diagnostic stack under malformed traffic, demonstrated compliance with WP.29 ISO SAE 21434, and created reusable fault injection scripts for regression testing. So these are the various types of outcomes and learnings that are emanated from this the entire project. Thank you.